Good morning, good afternoon, and good evening to all our webinar participants. My name is Christina Kraft, and I'm Marketing Manager at the Dräger work headquarters here in Germany. And I would like to welcome you to our international webinar about graphical screen interpretation in neonatal ventilation. Our presenter today is Thomas Krüger. Thomas is a Senior Product Manager at Dräger's headquarters as well. He's focused on the development of neonatal ventilators and attends important neonatal congresses and is in regular contact with key opinion leaders on respiratory care worldwide to discuss research and trends. Thomas has a deep understanding of the clinical challenges in respiratory care and knows how to translate this knowledge into technical specifications that guides the research and the development team here at Dräger. Today, he is sharing his knowledge on the basis of graphical screen interpretation by using examples of the device Babylog VN800 and VN600. And now it's time for Thomas to start with his presentation, and I would like to hand over to him and wish you a lot of fun and a lot of new insights.
Thank you, Christina, for the introduction. So let us look at the presentation now. So I put my presentation into three parts, basically. The first one is focusing on the understanding of pressure flow and volume curves. The second one will focus more on the implication of ET tube leaks in neonates. And the third part is an interactive part together with you, where we will together look at certain screenshots with curves in specific events or situations, and we will see how we can interpret these curves. Let me start with the first part, understanding pressure flow and volume curves. So you see here on this slide screenshots of different neonatal ventilators. We have here in the back, we have the Hamilton device, we have a Viasis device here, and as well we have a Gettinger Servo I device here, and here in the front we have a screenshot of the Babylog VN600. All these devices have one in common. They reserve a quite big area of the screen for graphical curves. So, and that for good reason, because these curves contain a lot of information, what it's all about during this presentation. So if we look closer to these curves, mostly these three curves are displayed on the ventilator screen. The top curve is the pressure. The pressure is a driving force for flow. So if there's no pressure difference, you will not see any flow moving to or from the patient. On the other hand, this pressure curve is more machine monitoring than a patient monitoring, because if you would occlude the Y-piece, this pressure curve would not change a lot. The second curve in the middle here is the patient flow. The patient flow is measured by a proximal flow sensor, ideally at the airway opening. And this is a pure patient monitoring, because here you see really the flow going and coming from the patient's lungs, and you can see as well the interaction between the ventilator and the patient. The third curve is then the volume curve. This is nothing else than the integrated flow curve. That means it shows how the volume over a cycle increases up to a certain tidal volume, which is the peak of this curve, and then comes back to the zero line if we have no leakage in the we have no ET tube leakage. Let us look for a moment to the flow measurement. So why are we using a proximal flow sensor in neonatal ventilation? The reason is simply illustrated by this diagram here. And we see here on the left side the ventilator with an inspiratory valve and an expiratory valve, a simplified patient circuit here on the left side, a simplified lung and respiratory system on the right side. And in between, we see the flow sensor, the proximal flow sensor. So below, you see here a formula which is expressing how the tidal volume which goes to the lung can be calculated out of the tidal volume which is delivered by the ventilator into the patient circuit, and the compliance of the patient circuit and the compliance of the respiratory system. So let's apply this for an example. So if the tubing compliance is, for example, 0.7, which is quite normal for neonatal patient circuit, as well, the respiratory system compliance can have the same compliance of about 0.7, which is also not unusual. So if we would now use these two compliance values in the formula below, then the formula comes to this change. And so it comes to 1 divided by 1 plus, and this term becomes 1 as well. So this then the whole formula turns into this formula, which means the tidal volume in the lung is just half of the tidal volume what is delivered to the system here from the ventilator side. And this is understandable because you can imagine that the volume distributes freely over the compliance of the patient circuit and the respiratory system compliance. So half of this volume stays in the patient circuit and the other half goes to the lung. So it's basically driven by the relationship of these two compliances, how much of the tidal volume delivered by the ventilator will really reach the lungs. As we never ever know, and we know at least that the patient circuit compliance is not constant, it is changing, yeah? And therefore, if we use a proximal flow sensor here in the middle in between this, then we can accurately measure what tidal volume is really going to the lung. How can we measure this? We have two flow sensors for the Babylogs in our devices. This is one Y-piece flow sensor and one ISO flow sensors. The ISO flow sensor has a lower dead space and therefore it's recommended for premature, extremely low birth weight premature babies. How are these flow sensors measuring the flow? They're using hot wire anemometry. This is a principle. So the principle is illustrated here. So if you have no gas flow, there are two hot wires which stay hot. And this is about 400 degrees Celsius if I speak of hot. So if now gas flow is passing these wires, then these wires are cooled down. And from the amount of cooling of these wires, the flow can be calculated. However, we do not need only to know about the flow size, we also need to know about the flow direction to differentiate between in and expiration. For this purpose, one of the hot wires is shaded by a very small bar. And this is displayed here much bigger than it is in reality. So this bar is protecting the one wire from cooling down if the flow comes from this direction and goes into this direction. So you see, this is protected from cooling down. This is the inspiratory time, inspiratory flow. So if now we see during expiration, the expiratory flow is not there, the second wire is not protected by the bar from cooling down. And so in this situation, both wires are cooled down in the same way. So therefore, this information can be used by the ventilator to differentiate between in and expiratory flow. So let's come back to the flow curve. The flow curve shows positive and negative flows. And there's no standard in the world which exactly defines how an inspiratory or expiratory flow shall be displayed. Nevertheless, there is all ventilators on the market displaying inspiratory flow as a positive flow value and expiratory flow as a negative flow value. So you can trust whatever ventilator you're using that this is the case in all ventilators. So let us come now to a small exercise and to learn more about the relationship between pressure, flow, and volume. So in this example, we will go through one respiratory cycle. We are currently here at the beginning of an inspiration where the cursor line is displayed here. You see on the right side a simplified diagram of a lung, airway, and an ET tube with a proximal flow sensor. And you see 2 points. The one point is a blue point here. This shall illustrate the pressure at the Y-piece. And we see a green point, which is here in the lung. And this is something what you never can measure, and also Babylog cannot measure. But nevertheless, we can show this here in the diagram to better explain the relationship between the pressure, flow, and volume. So currently we see here at the beginning of an inspiration, there is still the pressure is still at PEEP level here, yeah, at the Y-piece, and also in the lung, the pressure is at PEEP level of the previous expiration. So with the next point here in the curve, we are now at the end of an inspiration. So we see the pressure is at the end of the plateau phase here, yeah, and we see that the airway pressure at the airway opening pretty fast increases and stays at this plateau level for a longer time. However, the lung needs more time to equilibrate to this pressure. So the green curve here is a little bit delayed following this pressure at the Y-piece. The reason for this is simply that the lung needs some time to equilibrate to this pressure, and therefore the flow is needs some time to fill the lung, really. So this is depending on the time constant of the lung and airways. So if we look at the flow curve, we saw or see here that the flow went up during inspiration and then decelerates down to 0. At this point in time where the cursor is, yeah, the lung has completely equilibrated to the inspiration pressure, and therefore the flow came down to the 0 line. And if we think in the opposite direction, we can simply say that if we see a 0 flow, then we can be sure that the pressure, what we see at the airway opening, that in the lung we have the same pressure. Because otherwise we would see flow going into the lung or coming out of the lung. It's like in pressure conditions where you have a high pressure zone and a low pressure zone. And if you have this high and low pressure zone, then the consequence is wind. Yeah. If you have the same pressure, yeah, in both zones, yeah, then you will not see any wind because, yeah, there's the same pressure. So the next step in our cycle is now in the middle of the expiration. So here we see that the expiratory flow has started with a peak and now is on the decelerating way down to back to the 0 line. And we see the pressure at the Y-piece quickly is reduced to the PEEP level. However, the pressure in the lung is not at PEEP because the lung simply needs time to equilibrate to this new pressure. And as a sign of this, we see still flow coming out of the lung, and therefore we know that in the lung there is no PEEP at the current moment. So we need to wait longer until the lung completely equilibrates to the PEEP, and that would bring then the flow down to 0. And this is visible now in this situation here. Now we are at the end of an expiration. We have waited long enough, so the flow came down to the 0 line here again, and therefore we can be sure that at this point in time, also the pressure in the lung came down to the PEEP level. The volume curve as well is coming back here to the 0 line, even if we know that this is not really 0, it's FRC level of the lung. Okay, let us go now look for a moment at ET tube leaks and its implications. So where can we see ET tube leaks in the curves? So we see in this example screenshot here, I circled here the number for the percent leakage. This is currently the situation with an ET tube leak of 76%. Where can it be seen? In mainly two points. The one point is here in the flow curve. We see at the end of an expiration, we still see here positive flow. Means this is per definition a flow which is entering the lung. But in reality, we know that this flow is not entering the lung. This flow is going towards the patient, but is leaving the airways through the leak. Yeah. So, however, this flow is measured and it's also integrated. So look here, the volume, this is the inspiratory tidal volume. This was the expiratory tidal volume until this point here. And here now, the ventilator sees positive flow, which is escaping through the leak. And this is integrated, and therefore this volume curve goes up more and more and more. So it's only reset short before the next inspiration. So at this point, it is reset to 0 when the next inspiration happens. Okay, ET tube leakage. We now know how ET tube leakage can be detected. However, ET tube leakage is not constant all the time. In fact, it is changing a lot. It is changing with the position of the ET tube in the trachea. It is changing over time because simply the patient is growing and also the trachea is growing. It is changing over time because the patient is moving and all of this. So a leakage flow is never really constant over the longer time. But this is a problem because we are using the flow to trigger the ventilator and even to detect in pressure support, for example, to detect the end of an inspiration. So increased leakage flow can lead therefore to autocycling or to no breath termination. And even if we have properly adjusted the trigger level, the trigger threshold, and also the termination criteria for pressure support ventilation, if now the leakage is decreasing, then also high work of breathing can be the consequence to trigger a breath, low trigger success rate, high trigger delay times, and loss of tidal volume due to early breath termination can be the reason. So we can see this here. This shows these typical sensitive points here. So let's have a look here. This is the flow curve, and you see here, this is the pressure curve in the top. And we see now here a dark black line, which shall be the trigger threshold. And if now the flow from the previous expiration goes here through the 0 line and hits the trigger threshold, then the next inspiration is cycled. But this is without any spontaneous activity of the patient because this is simply driven by the leak through the ET tube leak. So, and also during the at the end of an inspiration, the flow can only come down to the leakage flow. It never will return to the 0 line. So, and if the termination criteria is adjusted below of this leakage flow, then the breath is virtually not terminated properly. So therefore, it would be needed to continuously readjust these two triggers, the trigger for in and the trigger for expiration. And as we right away knew that this is virtually impossible for any user to do this continuously, therefore Dräger has developed already 15 years ago a function which is called automatic leak adaptation, which is an automatic adjustment of the trigger threshold and the termination criteria based on the measured leakage. And this function is in all the neonatal ventilators active, and it's active all the time, so you can't switch it off. And it's, let's say, we have very good feedback over more than 10 years with this, so there's no reason really to switch this off. However, there is, in the newer devices, we have a new function which is called leak compensation. And this is related to the influence of the leak to tidal volumes. So I have here two pictures. On the left side, we see a picture during inspiration. On the right side, a picture during expiration. What happens if you have a leak, ET tube leakage, is the following. During the inspiration, the proximal flow measurement will measure an inspiratory tidal volume of 10 milliliters. But in reality, in the lung, there will be only 8 milliliters delivered. In this example, 2 milliliters are escaping during inspiration through the ET tube leak. These 8 milliliters then are exhaled during the expiration. And also here, we again, 1 milliliter is escaping through the ET tube leak, and 7 milliliters are measured by the proximal flow sensor as expiratory tidal volume. So we see the ventilator measures an inspiratory tidal volume and an expiratory tidal volume, and both are not correct, but at least the expiratory one is closer to the real tidal volume in the lung, to the 8 milliliters here. So therefore, it was good for many, many years to use the expiratory tidal volume for monitoring of the tidal volume. However, we tried to improve the situation, and so we developed a leak compensation algorithm. And this leak compensation algorithm is calculating the real tidal volume in the lung. So means this 8 milliliters. And this calculated tidal volume in the lung is then used to control, for example, the inspiration pressure and volume guarantee. So this function is in the meantime has been also described in one of the standard literature, which is the assisted ventilation of the neonate, or as well known as the Goldsmith-Korotkin. So it has also, it's also described there in this book. Now, two examples to show you how leak compensation is working. The first one is without active leak compensation. Here we see this is a situation of 57% leak. We see the leak here in the volume curve and in the flow curve. And we see as well here, there's an inspiratory tidal volume of 15.6 and an expiratory tidal volume of 8.2. If we now activate the leak compensation, which is shown here, now we can't see the leak anymore in the curves because these curves are compensated now automatically for this leakage. So we see now the volume curve comes down to the zero line again, and as well the flow curve comes down to the zero line. We see now there's still the in and expiratory tidal volumes of the previous picture, but now we have an additional tidal volume, which is a VT without an index. And this is now the lung tidal volume, so to say. It's leakage compensated, and this is 10.4. And so this is, I would say, this is the tidal volume what is closest to the real tidal volume. Is it perfect? No, it's not perfect because it's not measured, it's calculated. But on the other hand, this is the best tidal volume you can take if you have the choice between leak compensated, inspiratory or expiratory one. Just as a reminder, I have explained now leak compensation and leak adaptation. So the difference is leak adaptation is the automatic adjustment of trigger and termination criteria according to the measured leakage. This is all the time active, and it's available in all Babylogs, starting with the Babylog 8000, Babylog VN 500, and Babylog VN 600 and 800. The leak compensation is a correction of the displayed flow and volume waveform and the correction of displayed tidal volumes and minute volumes. It can be switched on and off, so it's not all the time off, all the time on, and it's available only in the newer devices, Babylog VN 500, 600, and 800. So we are now coming to the interactive part of my presentation. For this purpose, you have to take your mobile phones and you have to put in the following address in your browser, www.menti.com. And so we start the first question here. So the question is, what ventilation mode is active? And before we start the voting, because the screenshot might be not standard for you because you possibly are working with other ventilators, I will in a short moment explain what you can see here. We see here in the top the pressure curve, the flow curve, and the volume curve here. We see, and I have to explain this to all the people who are not using this Babylogs, the flow curve has two colors. So the darker color is the color for mandatory flow, caused by mandatory ventilation. And we have the light blue color for displaying of spontaneous activity of the patient. Then you can see here in the lower part of the display, you see all the settings. So in this case, FI2, inspiration pressure, inspiratory time, respiration rate, the PEEP, and the slope. And the slope is the ramping time for the pressure. So how fast the pressure is built up during an inspiration. So then usually you can see here in the top the ventilation mode, which is currently covered surely for this question. And here in the bottom, you can see as well 4 tabs with different ventilation modes, what you can select. Here on the right side, you see some measurements, which can be different in the different screenshots. But here in this example, we see the FiO2, the mean pressure, the PEEP, the minute volume, the respiration rate, and the tidal volume. So now I offered you the following choices. So number 1, if you think this is a pressure-controlled SIMV. Number 2, if you think this is a spontaneous CPAP. Number 3, if you think this is a pressure-controlled CMV, so controlled mandatory ventilation. Or number 4, if you think this is a pressure-controlled assist control ventilation mode. So we will now start our voting. Let's have a look to the screenshot again. So can it be spontaneous CPAP? You see here there are some cycling, pressure is built up and comes down to PEEP. So obviously this will not happen in CPAP, so therefore it can't be spontaneous CPAP, because in this case the pressure would be stable on the CPAP level and you would not see any inspirations. So can it be assist control? You see here the flow curve. So as I explained, this is an inspiration, inspiratory flow, expiratory flow. So we see the first breath here is answered by the ventilator with a mandatory inspiration. The second flow here, this is a spontaneous flow, inspiration, expiration. But we see this spontaneous activity is not supported by the ventilator. And therefore, it can't be assist control, because in assist control mode, every spontaneous activity is supported by the ventilator. So in this case, it can't be assist control. So the remaining are then pressure-controlled CMV or pressure-controlled SIMV. So the difference between these two choices is simply that the SIMV is triggered, is synchronized, and the CMV is unsynchronized. And if we look now to these arrows here, and we look that here an inspiration has started, and here the patient is already at the end of an inspiration when the ventilator suddenly kicks in and gives an inspiration. So not well synchronized. Here, there's even more extreme case. Here, this patient has taken an inspiration and here just wanted to start the expiration when the ventilator kicks in and gives a mandatory inspiration. So in this respect, the ventilator is not very successful because the patient is fighting against the ventilator and wants to exhale. And in this respect, it's the result is only a very short and small inspiratory flow, then followed by a big expiration flow here, until then the next pure spontaneous inspiration follows. So as well here we see it's not well synchronized. So therefore it's clear it can't be SIMV. So therefore PCCMV is a correct answer. Let us come to the next question. In this example, the PCO2 of this patient is very low. And the question is, what might be the reason for this? We see in the screenshot that we have two active alarms. The one active alarm is a minute volume high alarm, and the second active alarm is a respiration high alarm. We see as well that the respiration rate is at 98, and the minute volume is at 590 milliliters. So now the choices for correct answer is number 1, system is auto-cycling due to high leak. Number 2 is patient needs a deeper sedation. Number 3, there's water in the patient circuit. And number 4, this is simply the wrong ventilation mode. So please change the mode. So we give you a little bit more time to think about this. And now we will start the voting. So the first thing what you see here, if you look at the curves, that these, especially the pressure curve, is very, I call it bumpy. I mean, it's very, not very nicely. The shape is very irregular, And if you look now at the flow curve, this is mirrored as well in the flow curve, because if you have such an unstable pressure, at the Y-piece, surely also the flow, which is, because the pressure is, as what I said, the driving force for flow, this will be as well mirrored in the flow curve. And we see here the flow curve as well is not very stable. And this exactly is also the reason that because the flow curve is not very stable, this bubbling water in the patient circuit is causing trigger signals to the ventilator. And then the ventilator would simply give the next breath, because what you can see here in the top, we are in the mode assist control. That means every spontaneous activity, every trigger is answered with a mandatory cycle. That means every mistrigger here due to the bubbling water in the patient circuit will as well trigger a breath. And this will surely hyperventilate the patient in this case. So the monitored respiration rate is not a true rate from spontaneous breathing. It's reflecting the bubbling water in the expiratory limb of the patient circuit. Okay, why are the other answers wrong? Because, I mean, if it's not the patient, you could sedate the patient more, but this will not change the situation here because it's not the patient who is triggering the ventilator. And the system is also not auto-cycling because there is not really a big leak. We can see this here from the volume curves. The volumes return to zero line here quite well. And so therefore it's, oh, sorry, I misinterpreted this because we have a leakage compensation is active. Yes, but if we would display here the measured leakage, you would see that we have no leakage here, in ET tube leakage in the system. So it's really caused by water in the system. Okay, if we remove the water from the system, then we end up with this. So we see now respiration rate came down to the set respiration rate. Tidal volume is normal. Minute volume has come down to reasonable value. And if we look at the flow and the pressure curve, all these bumpy signals are away, and this looks very clean. Okay, next question. In this example, we have a patient where the blood gases are satisfying. They are okay. This patient has a body weight of 2.1 kilogram. And the question is, what settings can be improved? I have again 4 choices for you. Nothing, everything is perfect. This is number 1. Slope should be increased is number 2. Set rate should be decreased is number 3. And inspiratory time should be increased is number 4. So I give you a little bit more time, and now we start the voting. If we look here to the screenshot, if you look to the flow curve, you see that the inspiratory flow is not really slowly decelerating to the 0 line. You see a kind of, let's say, edge in the flow curve here, in the inspiratory flow curve. And that is a clear sign that you give this lung not sufficient time to equilibrate to the inspiration pressure here, to this pressure. So therefore, the flow came not down to the 0 line really. So you started, or the ventilator started the expiration too early. So, so this inspiratory time of 300 milliseconds are not sufficient for this time constant of the lung. So what we can do now, and we can increase now this number. And before I do this, I can show you here, this is a tidal volume currently. It's 9.9 milliliters. If we are now increasing the inspiratory time to 0.42, and now the flow comes really down to the 0 line with a decelerating flow pattern, now we see that the tidal volume also has increased. And this is important, it has increased not because we give more pressure. It just increased because we gave the lung more time to collect this volume. So simply give enough time during inspiration that the complete flow is entering the lung. Okay, we see maybe after we have done this now, maybe in reality, you could even reduce the pressure because less of tidal volume is totally sufficient for this patient. So this gives you the chance possibly to decrease the invasiveness of treatment here. Okay, let us come to the next slide, screenshot here. What might be the reason for the low minute volume? So we see here a screenshot with the minute volume alarm. We see, in fact, that the minute volume is displayed here, that it's relatively low. And additional information is here that this patient is a 1,350 gram patient. So you see the curves, you see the settings, so you see the mode, you see the most important measurements here. And now the choices are, in this case, number 1, the inspiration pressure is simply too low. Number 2, patient is exhausted due to high work of breathing. Number 3 is don't know. I need to ask a colleague. Number 4, this is a blocked DT tube. Or number 5, this is a wrong adjusted minute volume alarm limit. So we do not have any problem here. So we start the voting now. First of all, the minute volume alarm is not wrongly adjusted. So it's in fact really a small minute volume for 1,350 gram patient. However, it's not 0, and also the tidal volume is at 1.9 milliliters, which is far too low for this size of patient. But however, there's still some flow going into the lung and coming out of the lung. That's true. But however, it's the flow curve is a little bit has a rectangular form shape here. Yeah, you see this here a little bit. So it not has a typical shape of a flow inspiratory expiratory flow curve. And this is a clear sign for a partially blocked ET tube. So it's not fully blocked. If it would be fully blocked, then the ventilator would tell you, yeah, because there would not be any flow going to the lung or coming from the lung. But in this case, it's a partially blocked ET tube. And so this is the right choice and can be detected out of the flow curve shape here. So if we, after we have released the kinked ET tube here, then the flow turns into this shape again. Yeah, very clear natural shape of decelerating flow. And also the minute volume is then back to a normal value, and as well the tidal volume is back to 6 milliliters. Okay. Next question, very simple question. Is the patient triggering the ventilator here? And we have here a black bar below of the pressure line here with the pressure curve. And the reason for this is because here in this ventilator and the Babylog VN600, every trigger is illustrated by a small lung below of the pressure curve. So, and this, therefore, we cover truly this line. Nevertheless, I will help you a little bit with answering this question because I have frozen this curve at this point and put the cursor line at the beginning of the breath. So the two choices you have this time is very easy. It's yes or no. So is the patient triggering the ventilator? Number one is yes, number two is no. So we can start now the voting. So you see here, I put the cursor right before the pressure is built up here. You see in the pressure curve, yeah? And at this point in time, you see in the flow curve already that to the left of this cursor line, the flow has started already. You see a small triangle of this flow curve here to the left of this cursor line. And that means that first the patient started with an inspiratory flow. And this small inspiratory flow has triggered the ventilator. And then the ventilator, after that, the ventilator builds up pressure. Yeah. So to answer this question is very simple. Put the cursor to this point here where just before the pressure is built up. And then look, if you have flow before of this point, then it must be the patient who has triggered the ventilator. Yeah. If first the pressure is built up and then the flow is increasing, yeah, then it was a mandatory cycle, and the patient, the stroke was not triggered by the patient. Okay. By the way, there's also another possibly easier method to answer this question, because you see that we are in the mode assist control. And the backup rate here is adjusted here to 37. But the measured rate is 59. So it can't be the ventilator who triggers here. There must be some spontaneous activity. Otherwise, the rate can't increase to 59. However, so let's come to the next question here. We have this is the last question, what we can do here. So the question is very simple. What is this? So, and this curve is frozen here in this example. However, the cursor is not at a specific point here. But you see here pressure, flow, volume waveform, and the following answers are offered here. The number one, it's an ET tube leak. Number 2, it's an active expiration. Number 3, it's a too long inspiratory time. Number 4, there's water in the patient circuit. Number 5 is number 2 and number 3 are right. And number 6 is number 1 and 3 are right. So now it gets a little bit more complicated, but I'm sure you will make this as well. So we give you a little bit more, a few seconds more to think and to look at the curves. And now we start the voting. So where can we see this? So I put here 2 circles around the points where you can see this. So we see here a relatively long inspiration in the pressure curve. And we see in the flow curve here, first we see inspiratory flow. Then we see a certain expiratory flow. But then we see that this is not followed immediately by a next inspiratory flow, but as another expiratory flow here, and then a small inspiratory flow. And the explanation for this is that obviously here, the first expiratory flow here happens during the inspiratory time. You see, this is the ventilator is still during on the inspiratory plateau when here expiratory flow happens. And there's only one explanation for this expiratory flow. It must be the patient who is pressing against the ventilator inspiration and exhales against the inspiratory pressure. And this is truly as well explained as active expiration, or as well, we also speak about patient is fighting the ventilator. Yeah, so the patient is really expiring against the inspiratory pressure of the ventilator. So, and that is the typical pattern, what you see in the flow curve here. And only when the ventilator switches to expiration, you see a second expiration here, yeah, which is then, let's say, simply the release of the volume out of the lung, which is generated or which was held in the lung due to the inspiration pressure, which is then released to PEEP, yeah. So this was totally right. This was the last question. I had prepared a few more of questions, what you later can see in the PDFs, what we will send you, so you can as well look to this. For the moment, we have to go now to the end of my presentation. And because I want to give you the chance to ask questions. So please, if you have questions, please put these into the questions part of your control panel on the right-hand side. So simply type this in. I will read this for all, and then we'll answer these. So currently we see no questions so far. And I have to say, this group of participants obviously are not totally untrained in interpretation of flow and volume and of curves in ventilators, because the results was quite good. So congratulations. Most of you have really very good skills in interpretation of these curves. We still have no questions, so it seems to be quite clear, which is very nice. I hope that nevertheless you have learned something and it was good for you to participate here today. Yeah, we will send you not only the PDF, we will send you also a link to a recording of the session. So if you want to have a look to that, or want to watch this recording again, or want to show this to a colleague, you can do this later, and you can expect our email over the next 2 to 3 days. Okay, then I would like to thank you for participating in our webinar today. And we would be happy if you give us your feedback. So we will ask for this, your feedback. So we are happy if you answer this. And then hopefully we will see you another time for another webinar in the future. Thank you very much and goodbye.